Hi friends, today we discuss about the combination of resistors. In an electrical circuit, resistors can be connected into two primary ways, that is series combination and parallel combination. In a series circuit, the same current flows through all resistors and the total resistance is the sum of the individual resistance. In a parallel circuit, the voltage across each resistor is the same and the reciprocal of the total resistance is the sum of the reciprocals of the individual resistance. We know about the series combination of resistors. Series combination means resistors connected in series have the same current flowing through them and their total resistance is the sum of individual resistance. That is, the total resistance equals to R1 plus R2 plus R3 plus and so on Rn, where R1, R2, R3 represents the resistance of individual components. Next, we know about the parallel combination of resistors. Parallel combination means resistors connected in parallel have the same voltage across them and their total resistance is calculated using the formula total resistance that equals to 1 by R1 plus 1 by R2 plus 1 by R3 and so on 1 by Rn, where R1, R2, R3 represents the individual resistance. Next, we discuss about the resistors in series combination. When a number of resistors are connected end to end in succession is called series combination of resistors and all the circuit current passes through each resistor. In a series circuit, the same current flows through each resistor, meaning all the circuit's current passes through each one. In a series circuit, resistors are connected one after another, forming a single path for the current to flow. Since there's only one path, the current that enters the first resistor must also pass through the second, third, and all subsequent resistors in the series. The total resistance in a series circuit is calculated by summing the individual resistances. This is a diagram of a simple series circuit consisting of a battery and 4 resistors connected in series. We see the circuit components. Battery means voltage source V provides the total voltage V to the circuit. Positive terminal is on the top, current flows from positive to negative. R1, R2, R3 and R4 means resistors. Resistors are connected in series. Each resistor has a voltage drop across it V1, V2, V3 and V4 respectively. Points A to B. A is the starting point of current. B is the return point to the battery after current passes through all resistors. I means current. Current I is the same through all components since there's only one path. As we can clearly see that the components are cascaded in a single line. Thus, same current I will flow through all the resistors of the series network. While different potential difference exist between the various resistors of the circuit. It can be understood in a way that if the same current is flowing among all the resistors, so the drop across each resistor will depend on the resistance offered by each resistor in the circuit. Thus, we can say that in a series circuit, due to the presence of a single path, the same current flows through all the components, thereby giving rise to the existence of different potential difference means voltage across each component. Next, already we discussed about these points. Let R1, R2, R3 and R4 the resistance connected in series. When resistors R1, R2, R3 and R4 are connected in series, the total or equivalent resistance is simply the sum of all the individual resistance. Total resistance equals to R1 plus R2 plus R3 plus R4. The same current flows through all resistors. The voltage divides across each resistors depending on its resistance. Total voltage across the series connection is the sum of the voltages across each resistor. Let I be the current passing through the resistance. In a series circuit, the same current flows through all the resistors. That is, I1 equals to I2 equals to I3 equals to I4 equals to I. Let V1, V2, V3 and V4 be the voltages across the resistance R1, R2, R3 and R4 respectively, where V1 represents voltage across resistor R1. V2 represents voltage across resistor R2. V3 represents voltage across resistor R3. V4 represents voltage across resistor R4. The equations V1 equals to IR1. This is the equation number 1, where V1 equals to IR1. This is a direct application of Ohm's law. It means The voltage drop V1 across resistor R1 is equal to the current I flowing through it multiplied by its resistance R1. V2 equals to IR2. This is the equation number 2, where V2 equals to IR2. This is a direct application of Ohm's law. It means the voltage drop V2 across resistor R2 is equal to the circuit I flowing through it multiplied by its resistance R2. V3 equals to IR3. This is the equation number 3, where V3 equals to IR3. This is a direct application of Ohm's law. It means the voltage drop V3 across resistor R3 is equal to the current I flowing through it multiplied by its resistance R3. And V4 equals to IR4. This is the equation number 4, where V4 equals to IR4. This is a direct application of Ohm's law. It means the voltage drop V4 across resistor R4 is equal to the current I flowing through it multiplied by its resistance R4. The above equations V1 equals to IR1, V2 equals to IR2, V3 equals to IR3 and V4 equals to IR4 represents Ohm's law for the voltage drop across four resistors in a series circuit. They state that the voltage across each resistor V1, V2, V3 and V4 is equal to the current I flowing through the circuit multiplied by the resistance of that specific resistor R1, R2, R3 and R4. If R is the equivalent resistance between A and B points, then V equals to IR. This is the equation number 5. This is again a direct application of Ohm's law for the entire circuit or segment between points A and B. Already we know about the Ohm's law. Ohm's law states that the current I flowing through a conductor is directly proportional to the voltage V across it, provided the temperature remains constant. Mathematical expression V equals to IR, where V equals to voltage measured in volts, I equals to current measured in amperes, and R equals to resistance measured in ohms. The total voltage V equals to V1 plus V2 plus V3 plus V4. This is the equation number 6. It means resistors R1, R2, R3 and R4 are connected in series. The total voltage across the combination is the sum of the individual voltage drops. From 1 2, 3, 4, 5 and 6 equations. Simply 1, 2, 3, 4 and 5 equations substitute in the equation number 6. We get IR equals to IR1 plus IR2 plus IR3 plus IR4. Since the same current I flows through all resistors in a series circuit and using Ohm's law V equals to IR means V underscore N equals to I R underscore N. The above equation, the current I take common term from right hand side. Simply factor out I. That is IR equals to I into R1 plus R2 plus R3 plus R4. The above equation cancel I from both sides, assuming current I that is not equals to 0. Finally, we get R equals to R1 plus R2 plus R3 plus R4. This is the total resistance for resistors connected in series combination. Thus, the equivalent resistance R of the series combination is equal to the sum of individual resistance are connected. It means the equivalent resistance in series combination is the sum of all the resistance. Thus, the equivalent resistance will always be greater than the value of any individual resistance. Hence, we can conclude that the equivalent resistance will be larger than both the largest and the smallest resistance. Next, we discuss about the resistors in parallel combination. The image depicts a parallel combination of resistors in an electrical circuit. In this combination, multiple resistors are connected across the same 2 points A and B, providing multiple paths for the current to flow. We know the circuit explanation. Battery provides the electrical energy. RH represents a rheostat or variable resistor used to control the current in the circuit. Key means a switch that opens or closes the circuit. A means ammeter measures the total current I flowing through the circuit. V means voltmeter measures the voltage V across the parallel resistors. R1, R2 and R3 means resistors connected in parallel between points A and B. When the key is closed, the circuit is complete and current flows from the battery. The current I from the battery splits into three parts. I1 through R1, I2 through R2, I3 through R3. At a junction, I equals to I1 plus I2 plus I3. This is from Kirchhoff current laws. When two or more resistors are connected side by side across a single voltage source is called parallel combination of resistance. It means when multiple resistors are connected side by side with both ends of each resistor connected to the same 2 points of a circuit. It's called a parallel combination of resistance. In a parallel circuit, the voltage across each resistor is the same and the current splits among the different paths. In parallel combination, voltage V across each branch is the same. It means the voltage V across each branch is the same because all resistors are connected across the same 2 points. Current is different in different branches. The current I is different in each branch depending on the resistance of that branch. The branch with lower resistance allows more current to flow through it. Let R1, R2 and R3 be the resistance connected parallel between A and B. Let I1, I2, I3 be the currents in the resistance R1, R2, R3 respectively and is equal to the total current I. In the R1 resistor through current I1. In the R2 resistor through current I2. In the R3 resistor through current I3. Let V be the voltage across the resistance. Since the voltage across each resistor in a parallel combination is the same, let I equals to I1 plus I2 plus I3. This is the equation number 1, where I is the total current. I1, I2 and I3 represents the current flowing through resistor R1, R2 and R3 respectively. In each branch, current is I1 equals to V by R1. This is the equation number 2. I2 equals to V by R2. This is the equation number 3. And I3 equals to V by R3. This is the equation number 4. We know the Ohm's law. Ohm's law is a fundamental principle in electrical circuits that relates voltage V, current I and resistance R. That is V equals to IR. It states that the current I flowing through a conductor is directly proportional to the voltage V across it and inversely proportional to the resistance R. That is, the current I equals to V by R, where I represents current measured in amperes. V represents voltage measured in volts. R represents resistance measured in ohms. That's why I1 equals to V by R1. If a resistor R1 is connected across a voltage V, the current I1 flowing through it is equal to the voltage divided by the resistance. Next, I2 equals to V by R2. If a resistor R2 is connected across a voltage V, the current I2 flowing through it is equal to the voltage divided by the resistance. Next, I3 equals to V by R3. If a resistor R3 is connected across a voltage V, the current I3 flowing through it is equal to the voltage divided by the resistance. If R is the equivalent resistance of the parallel combination, then current I equals to V by R. This is the equation number 5. From Ohm's law, V equals to IR. The total current I is the sum of the individual branch currents. From 1, 2, 3, 4 and 5 equations, simply 2, 3, 4 and 5 equations substitute in the equation number 1. That is, I equals to V by R equals to V by R1 plus V by R2 plus V by R3. The above equation, we take common term V in the right hand side. Simply factor out V from all terms. We get V by R equals to V into 1 by R1 plus 1 by R2 plus 1 by R3. The above equation cancel V from both sides, assuming V that is not equals to 0. We get 1 by R equals to 1 by R1 plus 1 by R2 plus 1 by R3. Thus, the reciprocal of the effective resistance in parallel combination is equal to the sum of the reciprocals of the individual resistance. The above rule applies to any number of resistors connected in parallel. If you have more or fewer resistors, just extend or reduce the sum accordingly. This is our brief explanation of combination of the resistors. Thank you very much. Padmam Hyamam.